All right, welcome to physics lesson 5.03, where we start to talk about some of the unusual situations we run into and some of the things that you need to know, problems on an incline, multiple angles. So we're going to start off with a lawnscaper doing some lawn work when a 2 kilogram tire escapes from his wheelbarrow and begins rolling down this, bug me, rolling down a steep hill, 30-degree incline. That's a pretty steep hill. So we're in San Francisco. Sketch the parallel and perpendicular components of the weight vector, determine the magnitude of the components using trig functions, and then determine the acceleration of the tire, ignore friction. Boy, that's an awful lot of information from only having 2 kilograms and an incline. Turns out that's all we're going to need. Now, one thing I'd like to note ahead of time, if it's a tire, it's rolling, and that introduces some physics that we don't have our card for yet. We don't know how to handle that. So just keep in mind there'll be more to this problem later. Okay, so I'm going to use my little handy dandy guides, and I want to draw this free body diagram really big. So I'm going to start off. I'm going to give myself a little bit of a horizontal, a little bit of a dash line. That's going to be about 45. So if I'm going to do 30, now this is my surface. So this is the hill. All right, that feels like it's more like 45, but I was trying to do 30 degrees. I had to estimate. And we've got our tire up here. You know what? I need to put the tire a little further down or my vectors are going to go off the page. So, and I'm going to put it on as a block. This is more than likely going to be a part 1, part 2. I don't think I'm going to be able to do both of these problems in one video. Okay, so what are before I can start anything, I have to figure out what forces are going on. So take a second if you need to pause the video. All right, so hopefully you said the weight, and we have a surface and it's in contact with the surface, so there's a normal force. But if you said applied force, that would be incorrect. No one's standing there pushing the box. Remember, contact forces are forces that are touching, with weight, the gravity being the exception. So I only have 2 vectors here. So I'm going to pick so let's say the center of the box is here. So here's the thing. The weight vector is always directly down. F sub W is always straight down. All right, so but the normal force Fn is perpendicular to the surface. Here's the other thing. I'm not quite sure how big to make my normal force. So I'm going to wait until I do my motion analysis. And here's the other thing. So my motion is this direction, right? Because I'm rolling down the hill, but my weight vector goes straight down. My motion's this way. Am I accelerating? Have you ever watched something roll down a hill? Does it accelerate? Yeah, it sure does. So we have with acceleration. Well, I've got a problem. This is going to get messy, right? Because I have my normal force has to go this direction. So if I have 2 choices, I could do this coordinate system. And I'm going to draw this in pencil because I'm going to erase it. I'm going to draw it in pencil dark enough for you to see it. So my normal force is going to have to be here somewhere. I don't know how long yet. So if I use this coordinate system, my weight vector is going to be on my axis but my normal force isn't, so I'm going to have to resolve my normal force. Well, that's no big deal. But what happens if we were pushing this, if we were pulling this up the ramp, so I have an applied force, and at the same time I had friction acting? If I use this coordinate system, now I'm resolving all three of these vectors. Yuck. Do you want to do that? I don't want to do that. Well, how could we not do that? Let me erase this stuff first. What if I make this my coordinate system? Can I do that? Yep, I can. So when I have those three vectors that I just erased, those are all going to lie on axes, and the only vector I'm going to have to resolve then is my weight vector. So what we're going to do is we're going to practice using this tilted coordinate system. So my motion is this way, but my normal force is going to go this way. Does my normal force have any component of motion here? It doesn't. And I'm going to go ahead and I'm going to draw the normal force instead of trying to work it out. So this first time I'm going to kind of so there's my normal force. And I'm going to do, let me see, I'm going to pick an orange because it's kind of a faint color. And I'm going to do dashed lines to indicate my axes. So staying consistent with this. There's my axes. So this guy has to be resolved. When I resolve this, I have to drop a vertical and a horizontal. And if you actually have to turn your body, that's okay. Because this tends to like literally turn people on their heads. So I'm going to have over here F sub WY. And over here I'm going to have F sub WX. Well, don't I have to have an angle? You do. If you do, so if I draw this back out, I'm going to prove it to you this first time, and then after that, you'll have to just take my word for it. So if we take, let me see. I've got my 30 here. I drop this. I'm dropping a line here. So this is going to be 60. And I have bisecting here. Shoot, I don't remember exactly. I think I drew these too far apart. I did. Should have had this. Hopefully you can do enough geometry. If I had these a little closer together, it would have been easier to figure out to go that I'm going to have 30. This is going to have to be 60. That's going to have to be 30. So it turns out that whatever the angle is with my hill is also the angle that I'm going to need here for my weight vector. So to sum this up, the F sub W angle with the vertical axis is going to be equal to the angle with the horizontal. I didn't do that very elegantly, but this is the angle that we're after here and here. So, and what I was trying to do was use the geometry complementary angle, that the two angles on a 90 degree always add up to 90, or on a right triangle add up to 90. Okay, so I've got a normal force. I've got this FWY, I've got this FWX, and I don't know anything else yet. Well, we do know something. We know that FW is going to be 2 times 9.81, which is going to be 19.62. 19.62 newtons. So that means that if this guy is 19.62, when I solve for FWY, it's going to be hypotenuse 19.62. Now, can I use cosine function here? Here's the next big toe tripper. If I resolve against the vertical, here I have a sine function for my horizontal, and I have a cosine function for my vertical. So remember, sine is opposite over hypotenuse. So this is going to be 19.62 sine 30. And this is going to be 19.62 cosine 30. Negative, negative, positive. If I wanted to find the normal force, that would be positive. So look at my vectors here. If this is my motion, before I go there, if this is my motion and I have acceleration, what component, what portion of my force is providing acceleration? Did you say that guy? You should. It's the x component of my weight that's providing my mass and my acceleration. If you thought acceleration was going to be 9.81 meters per second squared, that's in free fall, guys. Remember, 9.81 meters per second squared is in free fall. This is going down a slope. So this is going to be 19.62 sine 30 equals 2 times my acceleration. This ends up being 9.81 equals 2a, and I find out my acceleration is 4.9 meters per second squared down the hill. If it had asked me for my normal force is going to be positive 19.62 cosine 30, which I believe works out to be 17. Let me double check that. Yep. So this portion is going to be a positive 17, and this is going to be negative 17. The reason I said I wasn't quite sure, you guys didn't know the value. What you understand now is that there is no motion in my vertical. According to this is vertical and there's no motion, so these two vectors need to be equal and opposite. There's a net force in the horizontal, which you have to remember, according to my coordinate system, the horizontal goes along the surface. All right, so what are our takeaways here? When we're on a hill, that changes the coordinate system that we're going to work with. Now, anything that the friction, applied forces, normal force are all going to lie on axes, which is nice, but my weight vector has to be resolved. I'm usually resolving against my vertical axis, so it flips my trig functions. The angle with that I make with the road is going to be the angle I'm going to have for the weight vector. Weight vector is always straight down. Normal force is perpendicular. And I have to do my motion analysis. So which of my vectors is providing my motion? Well, these are the two that are in the same direction. So that's how I'm going to get that. And that's pretty amazing if you think about it, that I got, now again, we're ignoring friction, not quite realistic, but having a mass and having an incline allows me to solve for this. All right, we're going to make this part 1. We're going to do the second problem in part 2, or this is going to be a super long video. All right, that's all for now.